Have you ever tried to add up an infinite number of things? I know, it sounds impossible, but it's something mathematicians do all the time. The real question is, what happens when getting to the answer is so painfully slow it's almost not worth the effort? That's what we're diving into today, the agony of slow sums.
Just let that sink in for a second. Imagine you needed to do 4 million separate calculations just to get a handful of correct digits for a single number. It sounds completely absurd, right? Well, today, we're going to explore exactly that kind of mathematical marathon.
So what we're really talking about here are infinite series, these sums that just go on forever. Now, some of them eventually converge or settle on a final answer, but the problem is some do it at a truly glacial pace, making the simple approach of just adding them up one by one pretty much useless.
And this guy right here, this is the star of our show today, the MRB constant. Now, look at that formula. It seems so simple, so innocent, doesn't it? It's just an alternating series. You add a term, you subtract the next, and on and on. But trust me, hidden inside that simple expression is a world of computational pain.
So what's this number? Well, that is how many terms from that simple-looking formula you have to add up just to get the 4th correct digit. And let me be clear, that's the 4th digit, not the 40th. This is the kind of ridiculous challenge we're up against.
And this picture, this just says it all, doesn't it? On the left, that's the mess we start with. It's the brute force sum bouncing all over the place, taking forever to make up its mind. On the right, that's the dream. That's our goal, an accelerated sum that just zooms in on the answer almost instantly.
All right, so just how slow is slow really? Let's take a closer look and quantify the frustrating reality of trying to solve this thing the hard way. To get some perspective, let's look at another famous slowpoke, the alternating harmonic series. It's a classic. To get just the 7th correct digit of its sum, you'd need to add up about 20 million terms. That's already mind-boggling. And here's the kicker. As the source material points out, our MRB constant is even worse. You know, one of the weirdest things about this constant is that if you just start summing it up, it doesn't even want to settle on a single number. You can see it in the graph here. The sums just bounce back and forth, getting closer and closer to two different values that are exactly 1 unit apart. The constant itself is actually defined by a little tweak that fixes this weird behavior. And just look at this climb for precision. To nail down the 2nd digit, you need over 1,700 terms. Okay, for the 3rd, that jumps to over 37,000. And for the 4th, you're looking at nearly 150,000 terms. This isn't just inefficient, it's practically impossible for any serious work. Thankfully, when a calculation seems impossible, that's when mathematicians get really creative. This brings us to our first major breakthrough, an absolutely elegant fix from one of the greatest minds in history, Leonhard Euler.
So the big idea here is something called series acceleration. And it's exactly what it sounds like. It's a whole toolbox of clever techniques that can take a slow, crawling series and transform it into a new one that speeds toward the exact same answer, just way, way faster. One of the very first and, honestly, most beautiful of these methods is the Euler transform. Instead of just naively adding terms one by one, it ingeniously reorganizes and recombines them. It's kind of like looking at the problem from a completely different angle, and suddenly, the answer just pops out.
And does it work? Oh, you have no idea. Let's go back to that slow harmonic series. Summing 159 terms the normal way gets you 2 digits. Whoop-de-doo. But if you apply the Euler transform to those exact same 159 terms, you get over 50 correct digits. That's not just an improvement, that is a completely different universe of efficiency. So what about our problem child, the MRB constant? Well, using just 60 terms, the brute force method gave us a measly 2 correct digits. With Euler's magic applied to those same 60 terms, we jump all the way to 22 correct digits. A huge leap forward for sure. But in the modern world, we can do even better. Yeah, Euler's method is absolutely fantastic, a real game changer. But for the kind of work done today, calculating millions or even billions of digits, we need even more powerful and sophisticated tools in our arsenal. One of the key modern insights is this brilliant subtraction trick. Researchers figured out the exact piece of the formula that was acting like an anchor, slowing the whole thing down. So they developed a way to mathematically pull it out, deal with it on its own, and then what's left behind converges like a lightning bolt.
This all leads to a powerful, modern two-part strategy. First, you find a way to calculate the individual terms of the sum much faster, using a super efficient approximation tool called apode kernel. Then, you take that stream of quickly made terms and you sum them faster, using even more advanced acceleration techniques. It's about being smarter and faster at every single step of the process.
And it's so important to get this. These methods aren't just random hacks that happen to work. As the source material beautifully puts it, they're grounded in deep mathematical theory. In other words, this stuff works because it's built on a solid logical foundation. It's elegant engineering, not just a lucky guess.
Okay, so we've talked about the slow way, and we've talked about a few of the faster, smarter ways. Now it's time for the main event. Let's put them all in a head-to-head race for the digits and see just how much difference these techniques really make.
This right here is the heart of our benchmark. For the exact same amount of work, summing just the first 60 terms, look at this incredible difference. Brute force gives us 2 digits. A slightly better method gets us 4. Then Euler's classic transform comes along and blows them away with 22. But then, look at that last line. A modern method like Crandall's formula gives us an unbelievable 111 correct digits.
And this bar chart just makes that leap so visceral. I mean, you can barely even see the bar for brute force. The jump from 2 digits to 22 is impressive, but then from 22 all the way to 111, it's a completely different league. This is the practical, tangible impact of developing better mathematics.
Okay, so we know how to calculate it with insane precision, but what is this number? What does the MRB constant actually represent? Well, it turns out this abstract number has a surprisingly beautiful, almost physical meaning.
Okay, get ready for this because it's pretty cool. That little piece of the formula, n to the power of 1 over n, you can think of that as the side length of a hypercube in n dimensions that has a volume of n. The MRB constant is what you get when you add and subtract these side lengths for a 1D cube, a 2D cube, a 3D cube, and on to infinity. It's like the universe's leftover change from building an infinite family of hypercubes.
And that just leaves you wondering, doesn't it? We started this whole journey with a frustratingly slow sum, and we ended up with this stunning picture of infinite hypercubes. It makes you ask, what other beautiful, hidden structures are just waiting to be discovered inside the numbers we think we already know? Thanks so much for tuning in.